Okay, guys, this is my first presentation. It's about deferred shading. This is the agenda. In my home, I implemented a little rendering engine. And in that engine, I applied this technique to decouple geometry from lighting. I'm going to explain. First of all, I'm going to explain a little about how lighting computations are done. Then I'm going to explain about color rendering and its problems. Then the advantages and disadvantages of deferred shading, some of the optimization that could be done there, and then a little portion of code and a video about a scene using the engine. Okay, first of all, lighting. As you know, we have three basic light types. They are directional light, point light, and spotlight. Directional light try to model the sunlight. The data this type of light needs is a direction, a color, and intensity. The point light, this scene is from Unified Theorem engine. Point light is different because it has a position, it has a radius, a color also, and also an intensity. And the last one is the spotlight. The spotlight is like a flashlight. It has a position and direction, and affects the geometry using two angles. Okay, how the lighting calculation is performed? Basically, it follows three different steps. This scene was rendered using my little engine. It's a scene with four meshes. A mesh that is a room and three spheres. First of all, we need to check which lights need to be applied to a particular pixel. In this case, I only use point lights. And for example, if a light, inside the light radius there is no geometry, then that light is not going to affect the geometry. So the first step is to check the lights that are going to affect the pixel. Then, if for example my point there is geometry inside my point light radius, we need to evaluate a function that is called bidirectional reflection distribution function. This function basically computes the amount of light that the surface reflects. And the three things that are needed for this function are the material properties, the surface properties, and the properties of the light itself. For example, some material properties could be the diffuse albedo. The first picture is the diffuse albedo. Another one could be the specular albedo. Maybe in another talk we could explain in detail what they are. But basically, diffuse albedo is used to model raw surfaces, and the specular is to model the light in smooth surfaces. Some surface properties could be the normals, the position. This texture stores a normal vector that are used for a technique that is called normal mapping. And obviously, we also need the properties of each light that I mentioned, the radius, the position, if it has the direction, etc. Okay, and once we know the lights that are going to affect the geometry, and also we compute the BRDF function, we need to apply the result of a light visibility calculation to all the pixels in the screen. So we are going to zoom the contribution of each light. For example, this area is in shadow, and there are different shininess in these other areas. Okay, what's for rendering? First of all, I'm going to explain the DirectX 11 pipeline. In my house, I use DirectX 11 because I like Windows and Visual Studio and the documentation of this API. but this can be done also in a very similar way with OpenGL. So the DirectX 11 rendering pipeline we are going to use is this one. We have the Vertex shader. Okay, first of all, we have the geometry. The geometry is done. We have vertices, which properties. The vertices build triangles, and the triangles build meshes. These meshes will pass through the Vertex shader that is executed per vertex. Typically, in the Vertex shader, we are going to do a task like coordinate space transformation, for example, from object to world, from world to camera, from camera to flipped or projection space. In this case, after the Vertex shader, we will send our geometry to the rasterizer. The task of the rasterizer is the following. In computer graphics, we have something called a frustum. That is like a truncated pyramid, composed by 6 planes: a near plane, a far plane, and four other planes. The rasterizer will clip or will discard all the geometry that is outside the frustum. Also, it will interpolate the properties that are stored in each vertex to each pixel. And also, it will project all the dimensional frustum into a 2-dimension rectangle. The rasterizer is responsible to send candidate pixels to the pixel shader. Why I say candidate pixel? Because not necessarily all the pixels that are sent by the rasterizer to the pixel shader are going to be rendered in the final image. Obviously, all the shaders can check information in constant buffers and in textures. In textures, you could store the material properties I mentioned before. After a pixel is performed in the pixel shader, it is where we perform or do the lighting computations. And there, the pixel is sent to the render target or the output buffer. That pixel should win what is called a C-depth test. So if the pixel is nearer the camera than a pixel that was previously in that position, it is going to win that battle and will be painted in the buffer. So this is a high-level pipeline description of DirectX 11. So what forward rendering does? For example, we could have a bunch of geometry. In this case, I have only a cylinder. It will go over through all the pipeline, and the rasterizer will send all the pixels of this cylinder to the pixel shader. Then in forward rendering, we are going to iterate over all the lights, performing all the lighting calculation I mentioned. And then in this case, because the output buffer is empty, all the pixels belonging to that cylinder are going to be painted there. Then suppose that I do another draw call in the same frame where I want to render a cube. The cube will follow the same pipeline, is going to perform all the lighting calculation in the pixel shader, and is going to be painted in the output buffer. And then, for example, I could do the following with this object, with this moon. As you can see, because the moon is nearer the camera than the cube, and the cube is nearer the camera than the cylinder, there are some pixels of the cylinder and some pixels of the cube that were overwritten by pixel of the moon and by pixel of the cube respectively. What that means? That means that all the lighting stuff that we did with these pixels of the cylinder are going to be wasted in computation terms, because they are not be seen by the user. So, which problem has forward rendering? In some interactive application like games some years ago, we didn't have a lot of different number of lights. But now, this screenshot, for example, is for Unreal Engine 4. We need to support a large number of dynamic light sources. So we cannot pre-compute the lights and store them in texture, for example, because the light moves. So that's one problem, that forward rendering was getting low FPS due to that. Also, with forward rendering, we have a large number of intersection tests to check if a light affects geometry. Because for each draw call that, for example, draw a portion of geometry or some geometry, we need to perform a lot of calculations, intersection and lighting calculation with all the lights in the scene. So in talking about big O notation terms, it could be seen like its complexity is big O of n multiplied by m, where n is the number of geometry or of the number of draw calls that we want to render, and m is the number of lights. Also, point light, directional light, and spotlight are a very simple light that in the past fill its purpose perfectly, but now people created new light types that are physically based, more correct than the basic light types, and also more expensive to calculate. So, for example, new types are tube lights, mesh lights, and area lights. Also, we have an explosion in the number of required shader permutations because, for example, if we want to put preprocessor directives in our shaders, we are going to do conditional compilation checking if, for example, if we want to use the technique texture mapping with directional light, we need to do something. Else, if we are using normal mapping with point light, we need to do other things, other computation, and the same with displacement and texture mapping with point light, etc. And also, we end with a lot of different shader files. If we, for example, don't want to do conditional compilation. So the main problem of all this is that lighting is tightly coupled with the rasterization of scene geometry. So the solution, or what Deferred Shading propose, is to separate the geometry rendering from the lighting rendering. So it proposed to do what is called a geometry pass, or several geometry passes, and then do a lighting pass. I am going to explain each one. First of all, remember that in the pipeline, we are outputting the pixel shader results to a single output buffer. In modern graphics APIs like OpenGL and DirectX, you could output data to several render targets. These render targets in Deferred Shading idiom are called the geometry buffers. What are the geometry buffers? The geometry buffers are simply textures that store different geometry and material properties. So, for example, we could output the diffuse albedo in one texture, the normal of the pixels in another one, the specular albedo in another one, and all the stuff that we want in different textures. And also, if possible, we could mix different information in the same texture, but in different channels. Because remember that each texture has for example, 100 pixels. And each pixel has different channels. For example, has 4 channels in the case you are using the RGBA format. So in the geometry path, we could send all the geometry in one draw call if they use the same material technique, for example, and then output the data in different render targets. Note that here I'm not including lighting information because I don't need it. So, for example, some very common geometry buffers are one to store the positions, another one to store the diffuse albedo, another one to store the normals, and another one to store the specular albedo. For example, one scene could store the following. This texture will store the positions of the scene. This one will store the normals. This one will store the diffuse albedo, and this one will store the specular albedo. When these 4 textures are sampled in the lighting path that I am going to explain later, you could end with this. Okay, remember in the geometry pass, we ended with several geometry buffers that contain different information about the material properties and the surface properties of the geometry. So in the lighting pass, I am going to send this geometry that is a full screen quad. What is a full screen quad? It's a rectangle that covers all the portion in my screen. This rectangle will not be discarded by the rasterizer. That's why I send this full screen quad. Because I need that the rasterizer send all the pixels of this geometry to the pixel shader. Note here that now I have lighting information in my lighting pass, and also my geometry buffers that are the output from the geometry pass. Then in the pixel shader, I execute all the lighting stuff. In what way? In the following. The pixel shader, for example, will execute per pixel. Suppose current pixel shader is executing this pixel. This pixel is going to sample information from its geometry buffer texture using the pixel coordinates. For example, in this example, I am sampling the diffuse albedo, the specular albedo, and the normal mapping textures. In the same shader, I'm going to include the sampling information with my lighting information. I'm going to perform lighting computation and sum all the light computation ending with this scene. So the contribution is then summed with the contribution of all the other light sources affecting current pixel. So what are the advantages of using this approach? The advantages are that the scene geometry is decoupled from the lighting. So I first render all the geometry into the geometry buffers, and then I use I use these geometry buffers to do the lighting pass. To iterate, I use these geometries and iterate over all the lights to sample the information that I need. So, for example, another advantage is that shading and lighting is only applied to visible fragments. Suppose that we are doing forward rendering. I do a draw call to render this wall. The geometry is this wall. As this is the first geometry that is rendered because it's my first draw call in my current frame, all the wall will be in the render target, and all the lighting computations are going to be computed. Then suppose that in the second draw call, I send the geometry of these two Chinese dragons. As you can see, these two Chinese dragons are nearer the camera than the wall. So they overlap a big portion of the wall. So a big portion of the wall do a lot of unnecessary lighting computation because they are overwritten by the Chinese dragon's lighting computations. That doesn't happen with deferred shading, because in deferred shading, my geometry buffers look like this, and the lighting computations will be done per pixel. So I will not be done a lighting calculation from this pixel belonging to the wall, and then for the pixel belonging to the dragon. I'm going to do only once. Also, there is a reduction in the render state. The render state, because I can sort my geometry by material technique or by lighting technique. So I could send this in one geometry pass, this in another geometry pass, this in another geometry pass, and then the geometry buffers to only one lighting pass. Another advantage, there are all techniques that currently are improved by modern hardware and modern techniques that were using indirectly. They were creating different render targets to fulfill its purposes. This technique, ambient occlusion, that uses a depth buffer to store the z coordinate of each pixel. This technique is shadow mapping that uses the same, and this is motion blur. Any question for now? I forgot to ask this before. Okay, I'm going to continue. Of course, not only sunshine and rainbows in deferred shading technique. If you don't have a lot of light in your application, you don't need it. If your engine is totally optimized for forward rendering, it will mean a significant engine rework if you want to switch to a deferred shading technique. Also, it requires more memory because in forward rendering, we are only using one render target, and here we are using a lot. Also, MSAA, that is multisampling anti-aliasing, that is a technique to smooth geometry borders, that is done by hardware, is costly and complex in deferred shading. We cannot do that by hardware. Forward rendering, yes, but not deferred one. And also, we need to use forward rendering for translucent objects. So many modern engines, for certain things, have a deferred shading approach, and for others, use forward rendering when needed. I am going to describe two optimizations to get better frame per second. Remember that in deferred shading, we are outputting our pixel data to many different render targets. The problem is that in the geometry pass, you need to output that data, the GPU, then the GPU needs to send these buffers to the CPU, and then in the lighting path, you need to send this data again. Sending and receiving things from CPU to GPU is expensive. So a thing we could have done is to minimize the amount of bytes that each texture needs. So the key is gbuffer memory footprint reduction. For example, in a greedy approach, suppose we have 4 different render targets, one for normals, another one for diffuse albedo, another one for specular, and the other for position. Suppose we are going to use 4 channels per pixel. In this case, this channel is going to store the normal coordinates, and this is unused. These channels are going to store the RGBA color of the diffuse albedo, the same for specular. And similar to normal, here we are going to store the different position coordinates. Suppose that we use 4 bytes per channel. So in each texture, we are going to need 16 bytes per pixel. So imagine the amount of byte that you are going to need if you are rendering in HD or in Full HD or in 4K. So the key here is to reduce this, to think how could you reduce the amount of bytes used in each channel. In the case of normal, instead of using four channels for the normal, we could. There are several methods to encode normals, the 3 coordinates in them, the 3 normal coordinates, into, for example, two coordinates. There is a method that, in my opinion, is the best that we can use. That is octahedral normal vector encoding. Basically, it is a function. You pass the 3 normal coordinates, and you receive 2 of them, and you only need 16 bits per coordinate, not 32. So you are going to store 2 bytes for each coordinate in your texture, and then you are going to sample that texture in the lighting pass and decode these 2 channels into the 3 normal coordinates. Another one is typically a color value goes in the range from 0 to 1. So you could use only 1 byte to store the color instead of 4. The same could be done with specular albedo because color 2. The difficult one is the position. The position, as we saw, I was using 4 channels to store the 3 coordinates. One of them was unused. So the unused one could be discarded. The position has the complexity that if you use less bytes, for example, instead of 4 for coordinate x, you use 2, you will have some problems in rendering. Because if your near plane and far plane are very far, then you are going to see some flickering in geometry that is far the camera. When you move the camera, you are going to have intersection problem. Many times, one geometry will look like it's near the camera than the other, and sometimes the opposite. But there are smart people that think algorithms, and they thought to store, instead of storing the 3 coordinates of the position, they store only the depth, the z coordinate. And when the near plane, with the near plane, the far plane distance, and the frustum properties, it could, using only the z coordinate, build the initial coordinate of the pixel. So we could reduce that to 2 bytes. So this is the final result. In the final result, we save a lot of space in each texture. So this is the normal A, the normal B, and all the other stuff. For example, in the game Infamous Second Son, in a paper that the publisher published, they show the different geometry buffer they were using. In total, they use 8 different geometry buffers. One only to store the depth, and others to store, for example, different normals, different coefficient for physically based rendering, and things like that. Question about the first optimization? Okay, I'm going to continue. Another technique is culling with screen aligned quads. If you remember, we were sending a full screen quad in the lighting pass. This is needed only for directional light, because directional light is going to affect all the pixels in the scene. But it's not true for point lights, because point lights are going to affect only a part of the screen. So, for example, this is the same scene where I was rendering a wall with many point lights. We could think that this scene could be simplified in this way. All the black area is not going to be touched by any point light radius, and this area are the point light radius. So, as we send to the Vertex shader a full screen quad, the rasterizer is going to send all these pixels to the pixel shader. But all the black area here will do unnecessary pixel computation, because the lighting is not going to affect it. So we should and we must save that computation. So in the case of point lights, instead of sending to the Vertex shader a full screen quad, we could send a list of vertices, where each vertex will store the position of each point light. So instead of sending a quad, we are going to send many vertices that, as I said, will represent the center of each point light. We are going to use the geometry shader. The geometry shader was introduced in DirectX 10 and in OpenGL 3, I think, and is used to generate or remove geometry. So in the geometry shader, we are going to expand this point to a quad, and the half quad width and height will be equal to the point light radius. You could think that this quad could be this quad is going to be like a bounding box for the point light in 2 dimensions, obviously. So the rasterizer, instead of sending all the pixel belonging to the screen, to the full screen quad that we were doing before, is going to send these little quads to a pixel shader. So the wasted computation is only the black area, because obviously the bounding box, because this is a bounding box of a sphere, there is some area that will not be affected by light. So in my case, using these 2 techniques, I don't remember the scene, but I was getting 150 frames per second, and after applying the G-buffer footprint reduction and the cooling with screen alignment quads, I got, I think, 350 frames per second, a lot of frames per second than before. So now I'm going to show some code. In this case, this is the Vertex shader code in the geometry pass. This is representing a basic geometry. My geometry, the vertex of my geometry only store a position and a normal. The output from the Vertex shader will output the position in clip space, the normal in view or camera space, and the depth. The depth is the z coordinate in view space in this case. My constant buffers that are the uniform in OpenGL are going to store the worldview projection matrix and the worldview matrix. And here I simply multiply. In this shader, I only do space coordinate transformation. And in the case for the geometry pass pixel shader, this is important to see. The pixel shader output will be 1, 2, 3, 4, 5 render targets. In this case, you don't see the diffuse albedo and the specular albedo because at this point I modified my little engine to be physically based. Physically based rendering, we need the normal, we need the base color. In one texture, we store the smoothness and the metal mask. The metal mask basically is a mask, is a binary value that will be 0 if the geometry is a metal and it's not a metal, and 1 if it is. The reflectance color and the depth. And here we are sampling, well, in this case is where I am encoding the normal using the octahedron algorithm. And then I am sampling textures. So this is the only thing that, for a basic geometry technique, the pixel shader does. These are my G buffers in my latest change in my engine.